Welcome back. This is the second segment of section 4.1. As you recall, in the last segment, we had just finished graphing y equals sine of x. I'll pick right up there. I was on page 4, so I'll go ahead and pick up and actually start doing some stuff for cosine so that we can at least have those two basic functions in mind when we talk about some other features. So let me just kick it over here real quickly. Got kind of getting slow in my old age here. Okay, so recall we had this graph of sine of x. So maybe I'll even kind of label it. This is y equal sine of x. So like we did before, let's talk about what happens with cosine. So remember, the values of cosine are very, very similar to the values of sine, right? You have 1, you have 1/2, square root of 2 over 2, square root of 3 over 2, 0, negatives of all those values. So without actually going back to a point table, I'm just going to start plugging those in. So I'm going to basically draw another graph, at least enough so you can kind of see what's going on here. So I'm going to kind of skip some values because they're very, very similar. Sine and cosine look almost identical. There's just a slight shift. So I'll have 2 pi. I'm just going to kind of do halves. So let's see, this is pi, 3/2 pi, and pi over 2. Okay, so recall that cosine, well, let me put some y values in here. So recall that cosine of 0 is equal to 1. So this is a point on that graph. And cosine of pi over 2 is actually equal to 0. Cosine of pi is equal to -1. Cosine of 3 pi over 2 is equal to 0. And cosine of 2 pi is equal to 1 again. Now notice we have this kind of back and forth sort of shape like we had with sine. And if you were to fill in all of the intermediate values, you would get exactly the same shape because it has the same quantities. It's slightly shifted. So if we were to kind of graph this, we would create this sort of smooth curve between these points. And if we were really good artists, that would look very smooth. So this is y equal cosine of x. Now here's something that I want to point out. Also, I mean, just kind of like before, you know, if we went any further, it would start to come back down on the edges. But notice what's going on here. Notice that we have the same basic shape, except that if we take this graph and slide it to the left by a quantity of pi over 2, we have the graph of cosine. If the graphs of two things are equal, then they are equal. So so we'll come back to this when we start talking about horizontal translations. But notice that we already have an equation, right? This is our so-called cofunction identities, which if I write them for radians, we have that sine of x is equal to cosine of x, sorry, not cosine of x, pi over 2 minus x. And it just so happens that to try to get this into that form of a f of x times of b times x minus c, etc., if we factored out a -1 here, you end up with cosine of -1 times x minus pi over 2. And remember, I said that this value here is representative of a horizontal shift. Now this one is representative of a flip because it's negative and the quantity is 1. So it doesn't really shrink or stretch, but it does flip. We're going to come back to this idea at some point just to kind of illustrate what's going on. But before we get there, I want to show you this observation, and we're also going to define a new thing related to functions. Like we've already kind of talked about what it means for a function to be periodic. Now we're going to introduce this idea of odd and even. So this is section 4.1, page 5 now. Okay, so this is another definition. A function f is said to be, I think I want to define even first, if for all x in the domain of f we have, or the following, let's say we have f of x equal to f of negative x. Now, that sounds very formal, and it should, because it is very formal. But this is something that you probably should recall from college algebra. There's some discussion about this concept of symmetry. So in college algebra, there are 3 terms that are used. There's symmetry with respect to the x-axis, there's symmetry with respect to the y-axis, and there's symmetry with respect to the origin. Okay, so just to kind of give you a little bit of graphic here. So let's do a sort of an x-y axis. So if you have symmetry with respect to the x-axis, then for every point above, there's a point below, right, for the function. Well, I mean, the problem with that is that this isn't a function, right? Maybe this is our graph here. So this is, there's problems with this, but this does have symmetry with respect to the x-axis, okay? But this is not a function. And the reason is that it fails the horizontal line test or the vertical line test everywhere. This is not a function. At best, it is a relation, but this is not a function. And so we will kind of ignore that part, that type of symmetry, because it doesn't really apply. All of our trig functions are in fact functions. And so this is sort of a peripheral discussion. But the next one that's kind of some interest is what's called symmetry with respect to the y-axis. Notice that that's when, if you have a point over here on the right-hand side of the y-axis, you'll have a corresponding point on the left-hand side. Similarly, you know, if we put a couple more in here, maybe it goes down here. I don't know. You know, something like this. So there would be sort of our function. Now this is actually a function, or could be a function. I mean, I suppose if you had some multi-values in there, it wouldn't, but this is kind of some interest. But notice that this is exactly what we mean by an even function, okay? An even function, if you were to say, I don't know, just pick some value of x here, well, the corresponding value of negative x is over here. And notice they have the same value of y, right? And that happens everywhere. And that's actually what's meant by symmetry with respect to the y-axis. This means the function is even as defined. So this definition we used up here, these two things are synonymous. A function is even if it has symmetry with respect to the y-axis and vice versa. Now, I'm going to hold off just a second with this and kind of define, if you can imagine, if there is an even function, there's probably an odd function. And without writing all of that stuff again, I'm going to say the criterion for an odd function and so most of the stuff up here implies the criterion for an odd function is f of x, and f of negative x is equal to negative f of x. And now recall from our discussion about a values, right? This would be like a equal -1, that if it's negative, it's a flip. So not only do we have a flip vertically, but we also have a flip horizontally. And that is something that in college algebra you called symmetric with respect to the origin. So let me just kind of give you a little small graph of that idea. This is page 6 now. So recall, we'll put a little bit on both x and y. So if you've got a point, say here, you need to have a corresponding point over here where both the x values are flipped and the y values are flipped. If we have maybe one here, then we'd have one there. If we have one here, well, we can't have that because that would create well, I mean, I suppose it's possible. We could create a relation, but I don't want to create relations. Let's say maybe we have one here, then there'll be a corresponding one down here. Maybe if we go a little bit further to the left and right. And so if I kind of connect the dots here, this is what we call symmetry with respect to the origin. Okay, and notice that if I pick any particular x value, there's a corresponding negative x value over here. And notice that the y values are, the magnitude's the same, except that their SIGN is opposite. So in this case, you really do have the situation where f of negative x is equal to negative f of x, right? So this, how did I say it before? I said this means the function is odd. As defined. Okay, so why are we doing all this? Well, it turns out that all trig functions are either even or odd, and so that kind of helps in our attempts to graph them. So I'm going to just pull for a second. I'm going to pull the graph that we made for sine and cosine. Sine was in the last segment. This is most recently. I want you to just kind of focus on cosine here a second. Now notice cosine starts to continue the other way as you go into negative values of x. So it really repeats sort of, it is really a mirror image over here. If we were to continue to graph this out, you'd see it come down to -1, then back up. And so just by looking at the graph, you can establish that cosine is an even function. So I'll just kind of put that here. Note, cosine is even. Okay. And if you look at sine, notice it has that kind of behavior that we referred to as symmetric with respect to the origin, right? It has this, not only if you reverse the x value, you have the same magnitude, but you have a negative y value associated with it. So it turns out that, in fact, sine is odd. And at this point, I'm going to write some identities. I'm not sure that these come out in section 4.1, but I'm going to go ahead and do them here. So there are what are called the symmetry identities. They're not particularly useful. We use them in a couple places to advance some other ideas, but they're not super useful. However, I'll just go ahead, for the sake of completeness, I'll go ahead and write them all down. We haven't introduced the idea of tangent, the graphs of tangent, cotangent, secant, cosecant yet, but I will just go ahead and write all of the cofunction, or all of the symmetry identities. So symmetry IDs. So let's start with sine. Well, all of them involve the trig function of a negative argument. So sine of negative x, because it's odd, will be equal to negative sine of x. And this is where I was talking about like trying to get rid of negative b values. You can do this by just throwing them, either they disappear or they come outside of the argument. Cosine of negative x. Well, since cosine is even, the SIGN on the argument simply disappears. And this, the symmetry of a function is the same as the symmetry of its reciprocal function as well. So it turns out that because sine is odd, cosecant is also odd. But for completeness, I'll go ahead and write these out. So tangent, it turns out, is also odd. And so tangent of negative x is equal to negative tangent of x. Its reciprocal function, cotangent, has the same characteristics. So cotangent of negative x is equal to negative cotangent of x. Then we go to secant. So secant is the reciprocal of cosine, and so it has the same sort of symmetry behavior. So it just simply becomes secant of x. It loses the SIGN. And then finally, cosecant of negative x. Same symmetry as sine, its reciprocal function, so we end up with minus cosecant of x. Now notice, most of these functions are odd. The two that are kind of oddballs are cosine and secant. But anyways, that's the symmetry IDs. I think they're maybe introduced in the next section, but I think it's valid to look at them now because we can do some stuff with the previous relationship that I wrote, which was that notice that cosine of x is equal to sine of pi over 2 minus x. Well, this happens to also be equal to sine of negative 1 times x minus pi over 2. And because sine is odd, that negative sign can pop right out, and we end up with negative sine of x minus pi over 2, which involves a vertical flip and a translation by pi over 2. And that's how those two functions are related. And it turns out that there's more than just that as well. I mean, this is just sort of the beginning. Okay, so let me move on to some additional definitions. So now we're focusing on the parameters that we had, the A, B, C, and D. So section 4.1, I think we're now on page 7. So let's look at the value A. So no, just recall a second. We're only talking about y equals a times f of x. We're going to ignore all the other parameters for a minute and just look at this one. So we want to consider values where a does not equal 0. So if a is equal to 0, this is a pretty boring function. This is y is equal to 0. But if it's not equal to 0, then you have some interesting things that happen. So for these functions, so for y equal a times sine of x, or y equal a times cosine of x, these functions, y will range from the closed interval negative absolute value of a to positive absolute value of a. And the reason I've got the absolute values is because a could be negative. And in fact, that happens quite a bit. So by using the absolute value, I strip the SIGN and then I artificially put it back in for the lower bound and the upper bound. This is a closed interval. So that's the range of y in both of these cases. Now, specifically for sine and cosine, this a value, or actually the absolute value of a, is called the amplitude. And you might think about what amplitude means. Generally speaking, that term means how far things range, right? Like how big or small they get. And this is more of a physics term, but it does creep in here a little bit. So it's kind of a magnitude by which this thing shifts up or down, which is relevant in this particular case, because that's exactly what's going on. So I want to just, so what happens when we change an a value? So we knew what sine looked like, sine of x. What happens when a is larger or smaller? So I'm just going to kind of give what's left here. I'm going to give sort of some graphs on top of graphs. So I'll start with kind of do everything for positive values. Not going to put a whole lot of stuff in here, but let's just 1 and maybe 2 here. I'm going to use a different pen so it's not quite so messy. But recall, for sine, we start at 0. We end up back at 0 at pi. We achieve a maximum at pi over 2. And we have a minimum at 3 pi over 2. So just like before, I'm not going to fill the entire graph in. You already know what it looks like. So we've got bing, bing. Again, I'm not much of an artist, so I'll end up making things look weird, but just slowly increases, turns the corner, comes back down, achieves its minimum, and right back up. So this is y equals sine of x. What happens when we make a, like say 2? Well, consider this for a second. Sine 2 times sine of pi over 2. So pi over 2, sine of pi over 2 is equal to 1. And if we double that, then it actually is equal to 2. So I'll just put that point up here. At 0, sine of 0 is 0. So it doesn't really matter what you multiply it by. You're still going to get the same value. Same thing's true at pi. Now, 3 pi over 2, the value is doubled, but it's negative. And then you're back to 2 pi. So when you have 2 sine of x, you end up with something that's a bit steeper here. It attains a higher value. And again, I'm not much of an artist. It's hard to do this without graph paper. But notice that it becomes larger. And so I'm going to label this one as y equal 2 sine of x. So as a gets larger, this graph stretches vertically, right? You get a vertical stretch that happens. If we had sine of 3x, well, it would go all the way up to 3 and all the way down to negative 3. What about if we have 1/2? So 1/2, it will actually kind of shrink. And so we would have sort of at pi over 2, sine of pi over 2 is 1, so 1/2 over 1 is actually 1/2. Similarly, for 3 pi over 2, we'd sort of split the difference, and we end up with this sort of shallow graph that has been shrunk in some respect. So I'm going to call this y equal 1/2 sine of x. So as x gets larger, or as x gets smaller, but positive, the graph is sort of scrunched down closer to the x-axis. As a gets larger, so 2 or 3 or whatever, it actually stretches in the y-axis. But notice we still have the same intercepts, right? It doesn't do anything this way, and that's because there's a different parameter for that. Now, what happens if we have a negative? Well, if it's negative, let's just look at maybe say y equal negative sine of x. That's a flip, and we can see what happens there. So at 0, it's 0. at pi over 2, well, pi over 2, sine of pi over 2 is 1, so negative 1 times 1 is negative 1. At 0, at pi over 2, we're back to 0. And at 3 pi over 2, well, sine of 3 pi over 2 is negative 1, so negative 1 is actually positive 1. I'm going to put the point up here. And then we're back down there. So we fill in the gaps here. This would be y equal negative sine of x. And so what's going to happen is that if a gets larger but negative, this will actually stretch, right? It will stretch in the y axis. It'll get farther and farther away. So if we were to look at y equal negative 2 sine of x, all of these values will double. Y equal minus 2 sine of x. Okay, so there's sort of a big picture of what happens with different values of a. Negative produces a vertical flip. Larger values of a in magnitude either stretch or shrink. Well, the larger values stretch, smaller values shrink. So that's kind of the big picture for A. I'm going to, in the next video, I'm going to start talking about what B does. But notice, just if you pause for a second, maybe you notice that the difference between negative sine of x and sine of x is just a shift, right? You're just taking this hump, if you will, and sliding it over there, or vice versa, right? So it turns out that there's a whole bunch of identities, but there is an identity that relates sine to itself, right? So it turns out that minus sine of x is actually equal to sine of x minus pi, which is not terribly insightful, but is something nonetheless. Okay, so I think I'm getting a little long on time here, so I'm going to stop this video, but I will see you in the third segment.